Newton's understanding of gravity was good enough to get us to the moon. Ever feel lost in time, wondering if we really get what it is? Well, Newton's find is more than just an idea. It's a key that might open up the secrets of the universe, showing us a cosmos that's way wilder than we thought. How does Brian Cox's new idea mess with what we think about time? And what could it mean for how we see things? Come with us as we check out Brian Cox's fresh, mind-blowing idea about what time is in the huge cosmos around us. There are puzzles waiting to be solved, and a lot have to do with time and gravity, both big parts of our lives. Imagine a world where time acts weird, can slow down or speed up. Also, the force that keeps us on the ground might not be what we believe it is. This is where Albert Einstein's relativity theories come in. They give a new take on time and gravity. Einstein, a name everyone knows, gave us a new way to look at the universe with his relativity theories. His work helped us get how time acts in different situations, like when things move super fast. It all started in the early 1900s when Einstein shared two big ideas: special and general relativity. Special relativity from 1905 changed how we see time and space. Simply, it says the rules of physics are the same for everyone who isn't speeding up, no matter how they're moving. This idea brings up things like time stretching or slowing down under some conditions. A cool thought experiment to explain time change is the light clock. Imagine you're in a spaceship going super fast, close to the speed of light. Inside, there's a light beam bouncing between two mirrors. Physics says light speed stays the same for everyone. So, the light seems to make a longer angled path for someone outside the ship. The time it takes the light to travel this path should be the same for both people, inside and out. But since the path is longer for the person outside, it looks like it takes the light longer to finish its trip. This time difference is what Einstein called time change. Time goes slower for the person moving compared to the one standing still. So time acts different based on your speed. Knowing how things change when they move fast or relativistic effects isn't just a thought. Scientists use big machines like the Large Hadron Collider to push particles close to light speed. When things move this fast, we have to think about time in a special way to get correct predictions and measurements. Einstein shared special relativity in 1905, and it flipped how we get the universe, mostly about time and movement. This idea goes against what we might think. It says physics rules are the same for everyone, even if they're not still. This is different from what we feel every day, where we think if something's moving and we add speed, it just gets faster. But Einstein says there's a top speed, the speed of light. With this in mind, things that look like they happen at the same time for us might not look that way to someone zooming by close to light speed. Another idea from this thinking is length getting shorter. This means something looks shorter in the direction it's moving when seen from a still spot. Also, there's the famous equation E equals mc squared, showing energy and mass can change into each other. This is key for seeing how tiny particles act when moving fast and for explaining stuff like nuclear reactions. In real life, special relativity isn't just a thought. We depend on it in tech like GPS. When GPS satellites send signals to your device, they're moving. Because of this, time acts a bit different for them. If we didn't think about time changing in our GPS math, your location info would be way off. So special relativity teaches us time isn't always the same. It depends on how things are moving. This messes with how we usually see time and space. It's like our usual take on the universe is a bit wrong. Time isn't set. It's changed by movement. Some basic ideas like light speed being steady and how energy and mass connect have been proven many times. But there's more. Einstein's general relativity from 1915 goes deeper into how gravity and the universe's structure connect. It changes the usual idea of gravity as just a force that pulls things. Instead, it says gravity comes about because space and time are bent or curved. It's like saying gravity isn't an unseen force. It's just how things move in the universe. Per Brian, general relativity needs thinking of the universe as 4 parts, 3 space and 1 time. Big things like stars, planets, and even us bend space and time around them. This bend is what we feel as gravity. Imagine spacetime as a big stretchy sheet. When something heavy like Earth is on it, it makes a dip. If you put something smaller like a ball near Earth, it rolls to the dip. This is like how things act with gravity, not because of a force but because spacetime bends. General relativity explains how things move in our solar system, like planets circling the sun. It can guess the paths these planets take, like how Earth makes a circle around the sun. This is different from the old idea of gravity just pulling things together, which couldn't explain planets. Well, the new idea is space and time are bent like a bendy fabric, which fits better with what we see. A big event showing general relativity was right happened during a solar eclipse in 1919. Sir Arthur Eddington led a team to watch how light from far stars bent as it passed the sun. The theory said the sun's weight would curve the starlight a bit. The watchings proved Einstein was right, showing the theory was good. Just like movement can change how we see time, gravity affects time too. Where gravity is strong, time goes slower than where it's weak. So if you stood near something heavy like a black hole, your clock would go slower than one far away from the heavy weight. General relativity brings up black holes, spots where gravity is so strong even light can't get away. The edge of a black hole is called the event horizon, and it's where there's no going back. Once something crosses this edge, it's pulled into the black hole forever. Einstein's general relativity has big effects on the universe's structure. He first added a term called the cosmological constant to his equations because he thought the universe didn't move. But when he found out the universe is growing, he called this a big mistake. A growing universe is key to the Big Bang theory, which tells how the universe started. Another big idea of general relativity is gravitational waves. These are bends in space and time caused by heavy things moving fast, like when black holes join. In 2015, scientists at LIGO spotted gravitational waves, adding proof to Einstein's theory. Over time, scientists have done tests to check general relativity, and it's always been right. Watching planets, light bending, or spotting gravitational waves, general relativity stays a good and sure idea. Saying gravity is a myth might sound wild, since we feel it every day. But in physics, it's normal to question and think about old theories. Scientists like Brian often wonder about usual ideas. In gravity, some have new ideas. One theory is modified Newtonian dynamics or MOND, saying gravity acts different at low speeds, mostly in galaxies without dark matter. Instead of unseen matter, MOND says gravity gets stronger at slow speeds. The talk on gravity also has dark matter and dark energy added to explain space stuff. Some say these ideas might not be needed, and other thoughts can explain what we see. Some scientists who don't agree with Einstein's gravity look into new stuff, like theories with unknown particles or forces that could change gravity. It's good to know that in science, new ideas aren't just thrown out. They're tested to see if they hold up. For example, Einstein's idea of time as a four-part thing, where time travel is held back by light speed, has been looked at with ideas like wormholes. Stephen Hawking's chronology protection makes time travel into the past unlikely in physics. New tests and watchings aim to see if these new theories can explain gravity in a way that fits what we know. But many ideas haven't really replaced the known rules of gravity. Questioning ideas is key for science to grow and get a better understanding of the universe. In gravity theories, general relativity is still the most important. Even with new ideas, it keeps doing well and explains stuff like planets and light bending. General relativity lasts because it's simple and fits with a lot. Einstein's special relativity says time can change based on your speed. Let's see how this hits real life, mostly in space. Moving in space is fun but hard because space is big. Light speed is the fastest. So moving between stars is tough even with good tech. To get how time changes when moving in space, think of the twin thing. One twin stays on Earth, and the other takes a fast trip to a far star. When the space twin comes back, they find they've aged slower than the Earth twin. They've moved into the future. Time is big for space travelers. The longer the trip, the slower time moves. If astronauts went to close stars, where time slows a lot, they'd age slower than people on Earth. This might sound like a story, but it's real. Imagine humans sending people to a far star. The trip could be years even if they go fast. The astronauts would feel time slower because of time change. But from Earth, more time would pass. Time change hits tech too. Computers and communication on ships have to think about time change to work right. Space moving has body problems like being alone, getting hit by space waves, and being far from Earth for a long time. In daily life, we see time change in GPS. GPS needs right signal times from satellites. Since these satellites are in motion, they experience time dilation. So it's important to include it in the calculations for the readings to be accurate. Not thinking about time change would mess up driving. Now, why do we only go one way in time? Time controls our lives, going from past to now to future. This one-way trip is part of us. But why? To get this, we look at entropy, how messy things are. Entropy, tied to time's direction, tends to grow as time goes, pushing time to go one way. The second law of thermodynamics says entropy will grow or stay the same in a closed area. Entropy likes to grow. It never goes down by itself. The nature of time, a deeper exploration. Time, as we perceive it, is intricately linked to the concept of entropy. Entropy, a fundamental principle in thermodynamics, measures the level of disorder within a system. The second law of thermodynamics states that in an isolated system, entropy tends to increase over time, leading to a progression from order to disorder. This principle not only governs the behavior of physical systems but also provides a framework for understanding the unidirectional flow of time. Box learning. To illustrate this, consider the analogy of a sandcastle. A sandcastle represents a state of low entropy, characterized by a high degree of order and organization. Over time, due to natural forces such as wind and erosion, the sandcastle will degrade into a sandpile, a state of higher entropy. This transition exemplifies the natural tendency of systems to evolve towards greater disorder, reinforcing the concept that time flows in one direction, from past to future. Box learning. Gravity and the fabric of spacetime. Building upon Einstein's theory of general relativity, gravity is not merely a force but a manifestation of the curvature of spacetime caused by mass and energy. Massive objects like stars and planets warp the fabric of spacetime, and this curvature dictates the motion of objects, including light. This revolutionary perspective shifted our understanding from viewing gravity as a force acting at a distance to recognizing it as the result of spacetime geometry. A compelling demonstration of this concept is the observation of gravitational lensing, where light from distant stars bends around massive objects like galaxies. This bending occurs because the mass of the galaxy curves the spacetime through which the light travels, altering its path. Such phenomena provide tangible evidence of the dynamic interplay between mass, energy, and the structure of spacetime. Black holes, singularities in spacetime. Among the most intriguing predictions of general relativity are black holes, regions of spacetime where gravity is so intense that nothing, not even light, can escape. At the core of a black hole lies the singularity, a point where the curvature of spacetime becomes infinite, and our current understanding of physics breaks down. The event horizon marks the boundary beyond which nothing can return, rendering black holes both enigmatic and captivating subjects of study. Recent advancements in observational technology, such as the Event Horizon Telescope, have enabled scientists to capture images of black hole event horizons, providing empirical data that supports theoretical models. These observations not only validate aspects of general relativity but also open new avenues for exploring the fundamental nature of spacetime and gravity. Time travel, theoretical possibilities and constraints. The concept of time travel has long been a subject of fascination and speculation. Within the framework of general relativity, certain solutions to Einstein's field equations suggest the theoretical possibility of closed time-like curves, paths through spacetime that loop back on themselves, potentially allowing for time travel to the past. However, these solutions often involve exotic conditions, such as the presence of negative energy or hypothetical constructs like wormholes. Physicist Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics may prevent time travel to the past to avoid paradoxes and inconsistencies. While time dilation, a relativistic effect where time passes at different rates for observers in relative motion, is experimentally verified and has practical applications. The traversal of time in a manner akin to science fiction remains speculative and unproven. Latest news and breaking headlines. The role of mathematics in understanding the universe. Mathematics serves as the language through which the laws of nature are expressed and understood. Physicist Brian Cox emphasizes that our experience teaches us that there are indeed laws of nature, regularities in the way things behave, and that these laws are best expressed using the language of mathematics. This perspective underscores the profound connection between mathematical structures and the physical universe, highlighting the predictive power of mathematical models in describing natural phenomena. Good reads. The development of mathematical frameworks, such as tensor calculus in general relativity, has been instrumental in formulating theories that accurately describe the behavior of gravitational fields and the curvature of spacetime. These mathematical tools enable physicists to make precise predictions and gain deeper insights into the workings of the cosmos. The expanding universe and its implications. Observations of distant galaxies reveal that the universe is expanding, with galaxies moving away from us at velocities proportional to their distance, a phenomenon encapsulated in Hubble's law. This expansion suggests that the universe had a singular origin, commonly referred to as the Big Bang, and has been evolving ever since. The discovery of cosmic microwave background radiation provides further evidence of the universe's hot and dense beginnings, offering a snapshot of the early universe and supporting the Big Bang model. Understanding the expansion of the universe not only sheds light on its origins but also informs our comprehension of cosmic evolution and the ultimate fate of the cosmos. Conclusion: the interconnectedness of time, gravity, and the cosmos. The exploration of time and gravity reveals a universe far more intricate and interconnected than our everyday experiences suggest. From the curvature of spacetime governing planetary motions to the enigmatic nature of black holes, these concepts challenge our perceptions and inspire deeper inquiry. As scientific understanding progresses, the interplay between time, gravity, and the cosmos continues to captivate and expand our comprehension of the universe's fundamental workings. Seeing how things go to mess helps us see times one way, like ice melting or stirring coffee.